Okay, let's jump right into this explainer by challenging a massive, almost default assumption in medical AI today. And that's the idea that deep learning is always the answer. I mean, we've all seen the headlines, right? Massive neural networks solving these incredibly complex problems. But when it actually comes down to clinical deployment, well, raw complexity can honestly be your biggest enemy. If you're an ML engineer working with clinical data, you know the absolute friction of getting black box models approved. Regulatory boards, doctors, they push back, and they push back hard. Let's be real, try handing a neurologist a completely black box model and just watch how fast you get shown the door. Which leads us to this exact question. Can we accurately predict the severity of a complex neurological condition, like Parkinson's disease, without relying on some opaque, unexplainable black box? According to a recent AI news article breaking down the highly anticipated arXiv preprint 2607.02553, the bottom line is this: neurologists and regulatory bodies simply cannot trust what they cannot verify. It makes sense, right? They need to see under the hood. They need to know exactly why a model is assigning a specific severity score to a patient before they even think about incorporating it into their assessment toolkit. So here is our agenda for today. First, the medical AI black box. Second, unlocking multimodal brain data. Third, interpretable models over deep learning. Fourth, hitting clinical accuracy targets. And finally, a developer playbook for medical ML. Section 1, the medical AI black box. So why does transparency actually matter so much more than raw complexity when we're building pipelines for limited clinical datasets? Well, the researchers behind this preprint made a very deliberate choice to avoid deep learning convolutional networks. Why? Because feeding raw 3D MRI volumes into a deep learning model introduces a staggering amount of unnecessary parameters. And when you're working with patient cohorts of under 100 samples, which, by the way, is incredibly common in specialized medical studies, those extra parameters severely amplify your risk of overfitting. Interpretable ML, on the other hand, gives us transparent feature mapping. It builds clinical trust, and it actually works efficiently on those smaller sample sizes. It's a win-win. Moving on to Section 2. Unlocking multimodal brain data. Okay, so if we aren't using deep learning to just automatically find patterns in raw pixels, what exactly are we using? Well, instead of opaque features, the research team, which was led by Aisha X. Andrade, focused on extracting handcrafted regional features. They took data from 28 participants, that's 24 individuals with Parkinson's disease and 4 controls, and they relied on 2 highly specific advanced imaging protocols. The first is QSM, or Quantitative Susceptibility Mapping. This is a big deal because QSM allows us to quantify local magnetic susceptibility in the brain. And in the context of Parkinson's, this is heavily influenced by iron deposition, especially in the basal ganglia. Now, medical professionals already know that iron deposition is a physical hallmark of Parkinson's pathology. So by using QSM, we're directly feeding the model a known, biologically relevant structural feature. The second protocol they used is ReHo, which stands for Regional Homogeneity. This is extracted from multiband multiecho resting state fMRI. The real beauty of this multiband multiecho approach is that it vastly improves temporal resolution and significantly cuts down on motion artifacts. Basically, ReHo captures the local synchronization of low-frequency brain signals. So by combining QSM's structural data with ReHo's functional data, the model gets a much more robust, completely non-redundant picture of the disease progression. Section 3. Interpretable models over deep learning. Now, having great features is really only half the battle, right? How you process them is what actually determines if a doctor will use your tool. To map these structural and functional inputs to the actual severity of the disease, the researchers tested 4 traditional regression models: ElasticNet, Random Forest, XGBoost, and Support Vector Regression. These algorithms are powerful for sure, but the key is they don't hide their math. For instance, the team found that while XGBoost and Random Forest handled nonlinear feature interactions really well, ElasticNet provided incredibly stable coefficients for the clinical variables. And here is where it gets really cool. By pairing these algorithms with SHOP analysis, which is a leading feature attribution framework, they achieved absolute transparency. The SHOP values mapped the model's predictions directly back to specific anatomical structures. They found that the cerebellar, thalamic, striatal, insular, and motor cortical regions were the primary drivers of the severity predictions. So there are no post-hoc approximation layers here. A neurologist can literally look at the output and see exactly which part of the brain influenced that specific score. Section 4. Hitting clinical accuracy targets. Of course, a transparent model is totally useless if it's wildly inaccurate, right? So let's anchor the statistical metrics from the study back to clinical reality and see how it actually performed. When they looked at the global fit, the full multimodal model, so that's combining the fMRI data, the QSM data, and the basic clinical variables, explained a massive 45.4% of the variance in motor severity. That is a highly significant statistical signal. It proves that objective neuroimaging biomarkers add measurable, real-world value beyond your standard visual motor exams. But as any medical developer out there will tell you, capturing variance or having a great R-squared value means absolutely nothing if it drifts away from clinical reality. And in the world of Parkinson's, that clinical reality is measured by the MDS-UPDRS Part 3 scale. This is the absolute gold standard clinical assessment scale that neurologists use to measure motor severity in patients. Basically, if the model's predictions don't align closely with this scale, they just aren't clinically useful. And this is where we hit the real aha moment of the research. The researchers defined a clinically acceptable error margin up front before doing the analysis, which they set at plus or minus 5 points on that MDS-UPDRS scale. When isolating selected QSM features alongside clinical variables, the model correctly predicted motor severity within that strict 5-point margin for 75% of the participants. It achieved the lowest mean absolute error among all their top performers. That right there is a stat a doctor can actually trust. Finally, Section 5, Developer Playbook for Medical ML. Listen, if you are building medical AI pipelines right now, regardless of the specific disease you're targeting, you really need to copy this framework. Based on this breakthrough, here is your developer playbook. Small sample medical ML requires strict validation hygiene. First, it starts with proper feature aggregation. Skip the raw pixels and go for handcrafted regional features to reduce dimensionality. Second, you need robust cross-validation. Third, it mandates integrating interpretability from day one, not just tacking it on as an afterthought. And finally, step 4, you have to track clinical proximity, like that 5-point threshold we just discussed, instead of just optimizing for a standard mean squared error. The best part is you can reproduce this exact type of pipeline using standard, widely available toolkits today. The researchers utilized neuroimaging libraries like FSL for handling the heavy lifting of preprocessing and crucial motion correction. They used NiLearn, which is just a phenomenal Python library, for extracting region of interest aggregates early on. And they utilized SHAP's tree explainer and linear explainer to generate those crystal clear audit trails required for clinical review boards. Oh, and please remember this crucial structural rule. Never, ever use simple train test splits on small patient cohorts. When you only have 28 participants, a simple split is highly susceptible to statistical noise and, worst of all, data leakage. Instead, you've got to wrap your estimator in a nested cross-validation loop. You can use scikit-learn to handle this natively. Just use the inner loop to tune your hyperparameters and the outer loop to rigorously evaluate how well the model actually generalizes to unseen data. By proving that interpretable handcrafted features carry incredibly robust predictive signals, this explainer leaves us with a final thought to really reflect on. Is your current medical ML pipeline transparent enough to actually be deployed? And when transparency finally becomes the absolute regulatory standard, which it will, how fast will your models reach the hands of the doctors who need them most? Focus on the features, focus on the interpretability, and the clinical trust will follow.